So we can summarize the information given. I'm being asked for moles, so I can put that in as a question mark. I haven't talked about this, and no one's asked, so I'm guessing it was obvious. I can't spell, apparently, and I spell moles without an E.
I think you addressed that in one of your hypotheses, don't you?
Oh, maybe I did. Okay, so I spell moles without an E, which symbol-wise is N.
It can be.
V is our volume, 2.34 liters. What is our pressure? Standard. Okay. Because we have the STP, we have standard temperature and standard pressure. What was standard pressure? 1 atmosphere. What is standard temperature?
Something Kelvin.
273.
So we're getting a couple things coming out of this. 0 degrees Celsius, which is equivalent to 273 Kelvin. Why do we convert to Kelvin?
Kelvin's all positive.
Kelvin is all positive, which means when I substitute into my ideal gas expression, my PV equals nRT, it makes more sense. Okay? Or I don't have to deal with that sign change on me. The last thing that I would need for PV equals nRT is I'd need to know what R is. R is 0.0821 liters times atmospheres per moles times Kelvin. Okay? We'll get to this lot of work in a second. Right? So we'll get to that in a second. Pressure, if we do our substitutions, it's 1 atmosphere over our R, and we'll talk about this in a second, 0.821 liters times atmospheres over moles times Kelvin, times our temperature, which was 273 Kelvin. This whole thing times 2.34, our volume. Everybody, at least one person saw what I did there. Does everybody else see what happened? Right? I just substituted in pressure, volume, R, and T. That was it. Okay, into that expression. Instead of putting the 2.34 in the numerator in next to the 1 atmosphere, I just pulled that out. Right? I can do that multiplication whenever and wherever I want as long as it gets done. Right? So if I go through and enter that into the calculator, that's going to be the same thing as taking 1 times 2.34 divided by 0.0821, 273. Okay. What happens with the units? Well, atmospheres, Kelvin, liters, and then my unit would be 1 over moles. Everybody see that from that big, long, nasty, complex thing? What is 1 over moles? Okay. Said another way, let's make mole a different number. Let's make moles 2. What is 1 divided by a half? You got a calculator. 1 divided by 0.5. 2. Okay. This would be the same thing as saying 1 over 1 times mole over 1. Mathematically, that works out. It comes out as moles. Whether or not you like the algebra behind that, unfortunately, is kind of irrelevant. It still comes out as moles. Okay? It is legitimate. It's fair. We're allowed to do all that. We'd enter that into the calculator, and we get what number?
2.
Because nobody did, or most people didn't do it this way. So what number does this way tell us?
104.
0, whoops, not a correct color. Let's try that again. I don't want red. 0.104. Can I get a second on that? Yeah.
Moles neon gas.
Moles of our neon gas. Okay. Did anybody else do a different method?
Yes.
What'd you do?
The other one.
Right? What do we want for an answer?
Moles of neon gas.
Moles of neon, what were we given? 2.34 liters of neon gas. If we set this up in our standard conversion, we'd want to get rid of liters of neon gas. We want moles of neon gas. Do I have a relationship between those? What is that relationship?
Yes.
1 mole.
1 mole over
0.4 liters.
22.4 liters. Okay. Am I allowed to use that?
Yes.
Why?
Because you're at STP.
I'm at STP and
And you're doing moles.
it's a gas. It's those two assumptions, STP and gas. Very easy curveball I could throw in is look at a molarity calculation, a solution, and say it's at STP. Who gives a flying crap? Okay? The STP is to make you think, oh, I need to be using this 22.4 liters, equal to 1 mole. If it's not a gas, you can't use it. This is a gas, so that is a valid statement to use. Okay? If you enter that into the calculator, what do you get?
0.104.
0.104 moles. What the heck? We get the exact same answer. Okay? Using entirely different numbers. 1, 22.4, or 1, 0.0821, and 273. Okay? That seems a bit bizarre. Okay? So what I want you to go through and do is take 1 and divide it by 22.4. That's it. That's all I want. What's that numerical value? Shh. But yes. What is 1 divided by 22.4? 0.045. Should be good enough. Okay. And now we've got in red up here, there's a reason why I color-coded that out. 1 divided by 0.0821 divided by 273. What do you get? 1 divided by 0.0821 is absolutely not going to be 0.0821.
You keep forgetting your
Okay. And we got to do 273. If you go through that problem, assuming that the 0.045 was a correct number, we will get the exact same value.
What?
Okay. So 1 divided by 22.4, which theoretically was not messed up, should be 0.045. 1 divided by 0.0821, return, divided by 273 will be 0.045.
So, like, what method will you recommend? Because I did it this way at the beginning.
So let's pause and take a consideration on what happened. We got the exact same answer, right? Okay. When was this equation valid? The 1 over 22.4. At standard temperature and pressure for a gas. When is PV equals nRT valid? When you have a gas. That's when it's valid. Okay. What is P in PV equals nRT?
Pressure.
Pressure. What is standard pressure?
1 atmosphere.
1 atmosphere. Check mark 1 for that 1 over 22.4. What is T?
Temperature.
Temperature. Which in our problem was 273, which happens to be standard temperature. Check mark 2 for this. R. Why is R in there? It's a constant. If I take into consideration the calculation of PV equals nRT at a given pressure or a standard pressure and a standard temperature, that then means all of those things get grouped into a single constant. That single constant comes out to be the relationship you're told to memorize. 22.4 liters is 1 mole. Okay? That expression or that simplification is only valid at those points because what happens if you change temperature or pressure? Those numerical values change, which then means that answer changes. You'd have to use PV equals nRT. Okay? So if you're at standard temperature and pressure, it's valid. Okay? The only times you're at standard temperature and pressure are in the class, and you're told that you're at those points. Any other time in the real world, you're not at standard temperature and pressure, which means you need to be using PV equals nRT. That is what we should be telling you to manipulate and use. Why do we not tell you to manipulate and use PV equals nRT as a whole?
It's a lot of work.
It comes with a lot more units, and it tends to confuse people already with the confusing topics of dimensional analysis. PV equals nRT removes dimensional analysis, and it steps back out into, here's a formula, use the formula. Okay? Which is something that you should now be like, oh, you're actually saying I can use a formula. Yes, I am actually saying you can use a formula. PV equals nRT will always work for gases that are ideal. Okay? Which means anything in this class. Kind of makes sense? Okay. So, two methods. You get to pretty much choose which one you want to use as long as you see those three little letters, STP. How else could I manipulate this question to allow your second super fast method to be correct, but then not make it quite as obvious? So let me clean all that up. I still want to go through and get to the same answer. How can I change the question to still allow you to use 1 mole neon and 22.4 liters, but remove the Q STP?
You could write in all of the values for temperature and pressure, and that would just be confusing.
Oh gosh.
At 1 atmosphere, or in, I don't know what adjective to use there, let's say in, 273 Kelvin. You now have your pressure and temperature. You might be going, oh, I have to use the ideal gas law, but the pressure and the temperature are STP. You can use the shortcut. Make sense? Okay. So anytime you see gases, you should be thinking PV equals nRT and then think, can I do a shortcut? Okay. Am I given standard pressure and standard temperature? If you are, then you can shortcut your way through it. Yes?
What does the N mean in PV and RT?
What is the what?
What is the N?
The N is moles,
Oh, what?
or it's number of particles
Oh, I see.
officially. But when we go through to solve, it makes more sense to have it in units of moles. So that's what R is defined as.
Always?
Is the unit for pressure always atmospheres?
No.
No. Okay. Is it typically written as moles and as atmospheres? Yes, because we don't want to have to memorize 20 different constant relationships. Fine. Other questions? Okay. So at STP, those are our temperatures and pressures. We could go through the ideal gas law, which we just talked about, or we could use that, silly mole volume relationship. Okay. Dalton's law of partial pressures, relatively simple concept. If I have this room filled with a whole bunch of different gas particles, the total pressure is going to be equivalent to the pressure from each of the gas particles. That's it. That's literally it. Okay? And it now looks fancy because I say P1 plus P2 plus P3. Those 1, 2s, and 3s are representing what? Each of the different gases within the room. They could also just as equally be each of the different particles in the room. Okay? It is typically referencing the gases because we tend to monitor based off of a group of elements or a group of compounds, not based off of single particles. Why do we not look at single particles? They're too small, so we'll look at the group of those particles. Okay, that's why we have moles. Okay, so a sample of noble gases, helium, neon, argon, and krypton. If the partial pressure of helium is 125 millimeters mercury, neon is 45 millimeters mercury. Gosh, I don't want to read all that. Some more numbers in millimeters of mercury. What is the total pressure of the sample?
Which one does that?
Okay, well, what is our total pressure supposed to be? This is where
Equal to the sum of the individual
It's the sum of the parts. So I have pressure from helium. I have the pressure from neon, pressure from argon, and I have the pressure from krypton. Okay. So now I just have to add all those numbers up, and I would get, what did you say the number was? 345. And you'd be wrong. Fix it. Millimeters of mercury. Now I would accept it. Okay? Why'd you do millimeters of mercury? Does it say the unit for pressure? It says what is the total pressure of the sample. Does it say you should be specifying it in millimeters of mercury?
You specify it in millimeters of mercury because the samples that you're given are all specified in millimeters of mercury.
Okay. It's technically a very crappy question because the question is not specifying the unit that it wants for your end. If it doesn't specify the unit, pick the easiest one for you to work with. Why is millimeters of mercury the easiest one for you to work with? Everything was given to you in millimeters of mercury. Okay. I do attempt to make sure that we don't have that ambiguity on exams. Okay. That's not the case across the board.
So what's the millimeters of mercury to atmospheres?
760 millimeters of mercury is 1 atmosphere. I honestly don't have it memorized.
So none of the answers will be in atmospheres.
True.
So we'd have to make that conversion. All right.
Yep. Yeah. Okay. Everybody kind of catch what's going on with that? Why did I pick noble gases? Why are they easier to work with? They don't react with anything. They're stable. Why is that important for looking at gases?
If they're changing, they kind of suck.
What was one of the assumptions we made about ideal gases?
No volume and no attraction.
No volume. Well, who cares? Noble gases. That has nothing to do with their reactivity, but you said no attraction between particles. Noble gases are already inert. They don't interact with each other. Noble gases make the most sense when looking at an ideal gas system. I could have picked any gas. The noble gases are the best choice in this case because they already don't react with things.
So if we're adding gases that were noble gases, so
then things could potentially go a little bit sideways in the real world.
it would change because 150.
We're now no longer ideal, is what would come down to it. We're no longer ideal. If we're not ideal, then all of the equations that we talked about snowball out of control and end up becoming invalid.
So
Okay.
this is the type of question we're looking at. Right. Are
It's
we looking at if you remove the millimeters?
Nope. All we're
Mercury
concerned
from
about here,
argon?
this was just a deeper evaluation of the question that's presented. That's all I was asking.
Right. So we're not trying to
Right.
find how many millimeters of mercury if that's missing.
True.
Given the
You would. You would.
Is that-
Okay. What I asked is why would I have picked noble gases instead of other gases? The noble gases are the most ideal of that situation. So what we're trying to do is dig a little bit deeper than just the superficial level and just make all of our assumptions. When we run gases, we have to make those assumptions, period. Why are noble gases the best choice? They make sure all of those assumptions are 100% valid with no questioning. Other gases would potentially make this system less real. Without more context, we can't make those adjustments. We'd have to run with what we've got. Okay? Absolute zero. Okay? The Kelvin scale is ultimately coming from looking at gases. Okay? What we can do is track backwards to what happens for our lowest temperature. And this is where we end up discovering that we have an absolute minimum, because if we go beyond zero, what would happen to our pressures, our volumes, or our temperatures? Or not our temperatures. Yeah, they would change, but they would change even if I went down or up. What happens if I go through zero? Through 0 Kelvin? What happens when I go through zero? So I go down below zero. What would my number be? Negative. Okay, well, why is that a problem?
don't like negatives.
Why does that become a problem for PV equals nRT?
It makes things flip.
You can't divide by 0.
Well, you can't.
Let's make the temperature negative. Why would that now all of a sudden make something weird?
Because then you would have to put it underneath. It's no longer.
It's not an inverse, it's literally a negative value.
Right.
Why is having a negative temperature make this system weird or make this equation weird? What are you saying?
It doesn't work in the real world.
So you're getting at the right idea. We can't have a negative value. Why? Someone said an idea over here.
This is a negative number of moles.
Right? Pressure is a positive value. Volume is a positive value. For those left and right to be equal, what does that mean the moles have to be?
Positive value. It has to be a negative.
It would have to be a negative. Can I have a negative of a substance? Okay, I can look at a negative or a change, but I can't have less than nothing. Okay? That doesn't exist. That doesn't compute. So I can't have a negative value of moles. Right? Well, what if the moles are then positive? Because you're right, you can't have a negative value of moles. What would that then mean? The moles have to be positive.
Change your temperature.
Keep pushing out. It doesn't have to be temperature necessarily.
You'd have to have a negative.
You'd have to have a negative number show up somewhere on the left-hand side of the equation, meaning you would have a negative pressure. Can I have a negative pressure?
A vacuum.
I can have a change, and a vacuum is not negative pressure. What is a vacuum? Zero pressure. Okay. Can I have, so pressure can't be negative. Can I have a negative volume? No. What does that mean? That means temperature has an absolute zero. I can't go negative on the temperature. Otherwise, this whole equation disintegrates. And all of the assumptions that we made that, for the most part, track pretty well, become completely and entirely invalid. Okay? That's why we know we have an absolute zero. Okay? That's where it's coming from. Questions about that? Okay. So now into the fun one. Okay, we took a nice sort of break away from dimensional analysis, and you're like, we didn't skip dimensional. We kind of did when we looked at our gases. But now we get to come back. All right, so let's ease into it gently. We're making some grilled cheese sandwiches. You need 1 slice of cheese, 2 slices of bread to make 1 sandwich. I personally think that's a crap sandwich, but, you know, that's all you need. Minimum, that's your minimum to make your sandwich. So there's our equation.
Okay. 1 cheese, 2 bread, 1 sandwich.
Okay? So we've now got our chemical equation. If we read the question underneath, there's our heat, by the way. If you have 5 slices of cheese and 8 slices of bread, how many sandwiches can you make?
4.
Okay? How are we doing this? This goes back to the bike example. People got sick of my bike example, so we had to switch to sandwiches.
Conversion. Lots
Okay.
of nice conversions.
Lots and lots of conversions. What do you mean? What did I do for my conversion?
Well, if we take 8 slices and we convert it into sandwiches, we get 4 sandwiches. But if we take 5 slices of cheese, we would get 5 sandwiches.
You need to start with sandwiches.
You can't have.
We don't know anything about our sandwiches. We can't start with sandwiches. We have none of them.
I misspoke. You need your first step.
Okay, I got you. You're right. Because I started the other way. I started the other way. Fair call out. So let me erase all that. Let's start again. First step, what do we want?
Sandwiches.
Sandwiches.
Number sandwiches.
What are we starting with?
Cheese and bread. We can choose cheese or bread right over here on the left.
Okay, so which one do you want to start with?
Bread.
Start with cheese. Sorry. We'll start with cheese. I don't want to write cheese, so I'm just going to say 5 cheese.
Over 1.
5 is nonsense.
Okay, officially over 1. I need to get rid of the cheese and turn it into
Sandwich.
sandwiches. We can make an argument for bread too.
Does it go either way?
We'll talk to me after class. Talk to me after class. All right. What's our conversion between sandwiches and cheese?
1 cheese equals
1 sandwich equals 1 cheese, which means I would get
5 sandwiches.
5 sandwiches. You guys told me 4. This says 5.
Right. Well, we're not done with that.
We're not done.
Yeah. Okay. We're not done. Fair enough.
So now
What do we
take
do?
slices of bread.
So we need to do
How,
bread.
how many sandwiches we get? And now we're starting with bread. What do we start with?
8.
8 breads over 1 times
Apparently we have bromine.
bread, sandwiches. It's a lowercase b. It's not
2
bromine.
breads,
Oh.
1 sandwich,
2 breads, 1 sandwich. This comes out as
4.
4 sandwiches. Again, you told me 4, but that says the most I can make is 5.
But you have to
You
have
take the
both.
lesser of the
So
two.
there's-
I have to take the lesser of the 2. Why do I have to take the lesser of the 2?
It's limiting reaction.
Because you don't have enough.
I don't have enough bread to make that 5th sandwich. I've run out of bread.
So whatever you have
Bread.
is the limiting reactant.
Whichever one produces the least amount is my limiting reactant. So bread is now my limiting reactant.
Well, that makes more sense than stupid bicycle thing.
Really? Okay. I'm okay with that. I'll start drawing pictures of sandwiches in the future.
That's just gonna make me hungry.
It would make me hungry too.
Hated the bicycle thing.
Runs out.
What's that?
Limiting reaction is the substance that runs out first.
The limiting reactant is the substance that runs out first. Okay. What would cheese then be?
Excess. Salt.
The cheese would be excess. Okay. Sometimes referred to as the excess reagent. What is reagent? Same thing as a reactant. Why do we call them something different? I don't know. No clue.
Because they're salt.
Because probably someone slurred their words when they said reactant and turned it into a G and then tried to pan it off as not a mistake. But no, that's actually a real word. Here, let me write it down some more so people believe me.
And then they believe that. Very much, very much.
That's science.
That's English. I'll talk to my English. I'll talk to my English partner about that. Does that make sense? Everybody okay with that?
Sure.
Right?
Why is
So-
that so easy in comparison to?
Why is that so easy in comparison to what we do in chemistry? So number one, it's familiar to us. We can watch somebody build sandwiches. We can see that sandwich built. Why is it so much more difficult when we move into chemistry?
Because we can't see.
You can't see it. Not only can you can't see it, you can't even feel it. You have no tactile response with the chemical world at that level. Okay? So we have to come up with weird models like sandwiches and say it's the same thing. It's not, but it's as close as we can get to try and make our human brain wrap around such tiny, tiny particles. Blame the brain. Find a neurosurgeon and yell at them, not me. Well, that depends. If they're working on you, don't yell at them.
Been there, done that.
Okay. Usually if they're working on them, they want you to yell at them, though, actually.
Yes,
They want to make
a
sure they...
response.
Yeah. In any case, sorry. Segue. Digression. We're okay with limiting reactants. Okay? At least at this level.
Yes.
So we're good to try and break it.
Burning lower.
So it doesn't get more complicated than that. So we're okay.
Well, yes, it does.
Okay? Well, I don't know.
Question, look the extra credit on it.
Okay? You tell me. Okay?
Very different.
Sodium carbonate plus water plus CO2 produces 2 sodium hydrogen carbonates. If I take 2 moles of sodium carbonate and I mix them with 2 moles of water and 1 mole of carbon dioxide, how many moles of sodium hydrogen carbonate are produced?
Some.
Okay. Some. Good answer. Okay. Whichever answer said negative, get rid of it. That was the wrong answer. Okay. So, and I appreciate that you guys are thinking through this, but we don't want to think. Okay? Write it down. The same process that we just did with the sandwiches, do with, what are we solving for? Sodium hydrogen carbonate. Exact same process. Follow that out. See what you get. If you got questions on where to start, raise your hand. I'll come to you. I'll also be kind of... Peeping Tom is not quite the right direction word, but I'm going to wander around and look at what you're writing over your shoulders. We have 3 separate reactants. We're given 3 separate amounts, which means we're going to have 3 separate solves. Just like with the sandwich, we had 2 separate reactants. We had 2 separate solves. Now we have slightly more complex because we have 3 separate reactants. We need 3 separate equations. All right? So I went through and attempted to underline or color code these. Hopefully it somewhat works. Right? All cases, I'm trying to find the amount of moles of sodium hydrogen carbonate that could possibly be produced. So that solve for all three cases is going to be aiming for the same unit. I want to know what the number is so I can now compare those. So I'll start with the first one. My bread, sodium carbonate. I'm given 2 moles of sodium carbonate, so I'll include my number associated with it because I'm given that. I now need to do a conversion because moles of sodium carbonate is not the same as moles of sodium hydrogen carbonate. That's why we call them different things. Okay? So I need a conversion factor where the moles of sodium carbonate as a unit, not the number, the unit cancels out. So that unit needs to show up in the denominator in my conversion factor. In the ideal world, I would find a conversion factor that takes me to moles of sodium hydrogen carbonate. Why do I want to go to moles of sodium hydrogen carbonate?
That's your end answer.
That's what I want for an answer. That's my ideal situation. You should always start with the ideal situation. Now the question is, do I have a conversion factor that allows me to convert between substances?
Yes.
Yes, there are 2 places that you can find conversion factors to convert between substances. Those 2 places are the balanced chemical equation or not the periodic table.
The words?
Not the words. The chemical formula. A chemical formula can allow you to convert between substances that are found where? In the chemical formula. Okay? There's no product, there's no reaction. I'm literally looking at a formula. Okay? So let's go back and look at an example for chemical formula because you guys seem to be balking at that one a little bit. So let's look all the way at the top because I'm not going to erase everything because I don't want to undo all the work I've already got. So let's just look at the top. Sodium hydrogen carbonate. How do I use that to convert to a different substance?
1 sodium, 1 hydrogen, 1 carbon.
For 1 sodium hydrogen carbonate, I have how many sodiums?
1.
1. That's out of the formula. How many oxygens do I have? 3. How many carbons? 1. The formula allows me to convert the symbols within the formula, the parts of that formula, to the whole. That's awesome. Okay? To use the chemical formula, I have to make sure that those parts are within the whole. So if I go down to what I'm trying to look at, my first conversion, is sodium hydrogen carbonate a part of sodium carbonate?
Yes.
Not at all. Okay? That's like saying bicycles have a part in a car. The components within a bike can show up in a car. Cars have chains. Bikes have chains. That doesn't make a bike a car. Doesn't happen. The parts are similar, but sodium hydrogen carbonate is not a part of sodium carbonate. It has similar parts that go into it, but it is not a part of. Okay, make sense? So, does the chemical formula conversion allow us to work? No. So I can't use a chemical formula. I must use the chemical equation. So we go back to the chemical, whoops. Let's actually find the chemical equation. Sorry. Might be useful if we had that back. We go back to the chemical equation. Sodium hydrogen carbonate being related to sodium carbonate. Does my chemical equation show those parts? Yes. What are the numbers associated with those parts? So I'm hearing 1 to 2. And even 2 to 1 I won't accept either.
1 sodium carbonate.
1 sodium carbonate. So I'd put the 1 in the bottom because what's in the bottom? Sodium carbonate. 2 sodium hydrogen carbonates because there's a 2 up in the chemical equation. It's the coefficient. Oh God makes me kind of happy because the way you said that was like a good thing. Not like, oh God! It was like, oh God, yeah. That was good.
Like I had it, and now it's more complicated.
Right? What happened? Our units, yeah, if you said, oh God, help me, that would be a problem.
Oh, thank the Lord.
Sodium, the moles of sodium hydrogen carbonate cancel from the equation. The unit I would be left with is moles of sodium hydrogen carbonate.
Which equals
Okay.
4 moles of sodium.
Now I can run the math. Okay? The units set this up. Now I can go back, and because I've placed the units in the proper space to do what I want, the numbers associated with those units I can run the mathematical expression for. In that first calculation, I have 2 over 1. And the next one, what do I have? 2 over 1. So I can take everything in the numerator and multiply it through. What is 2 times 2? 4. What is 1 times 1? 1. So my answer becomes 4. 4 what?
Moles of sodium hydrogen carbonate.
Take the unit work that you solved, take the numerical work that you solved, put them together, ta-da! Suspiciously harmonic. All right, the next one. Set up already. We're trying to convert the water across, the numerical values that get substituted in for that. There's a coefficient of 1 in front of our water. There's a coefficient of 2 in front of the sodium hydrogen carbonate. I can drop that in. If I follow the units, the moles of water cancel or convert. I would end up with moles of sodium hydrogen carbonate. My unit systems are now set. I can now go through and solve the numerics. This was 2 over 1 times 2 over 1, which is equal to 4 moles of sodium hydrogen carbonate. We did not technically already do this.
Well,
Why is that not technically repeated?
different unit.
It's a different unit, it's a different system. Don't start saying you did the same thing. You didn't do the same thing.
It's a whole other molecule.
Okay?
It's a whole new.
That's better than calling it a horse, but yes. Because it's chemistry? It's like a horse? Never mind. What did we start with?
What about a horse?
Moles of CO2. Do I want moles of CO2 in my answer?
No, moles of sodium hydrogen carbonate.
So moles of CO2 as a unit needs to show up in the denominator. What unit do I want to show up in the numerator?
Sodium hydrogen carbonate.
Where do I find a conversion factor that relates the moles of sodium hydrogen carbonate to the moles of CO2? From the coefficients of the balanced chemical equation. Now I can drop those numbers in. 1, 2. If we run through the calculation, it's 1 over 1 times 2 over 1, and this equals 2 moles of sodium hydrogen carbonate. Right? The result. Now we go back to the question, how many moles of sodium hydrogen carbonate are produced?
2.
2. I picked the lesser of those numbers because CO2 limits the equation. I can't produce any more.
I have a question.
Though, that's always a fun start. Yes.
I don't think that the question asked is asking what is the limiting reagent.
The question does not ask what is the limiting reagent. Okay. It's asking how much is produced.
So would you add them all up?
Okay, so that's an interesting question. I could potentially add all of those numbers. Okay? But with moles of CO2, what happens with the moles of CO2?
Oh, you can't do any more than that.
I'd run out at 2 moles of sodium hydrogen carbonate. I literally have no more CO2.
Okay.
So to answer this question, it's not asking for the limiting reagent, but to answer the question, what do you need to know? The limiting reagent. Okay? So it becomes an implied aspect of the question. You have to be able to tease that information out of it. How do you know you're being asked a limiting reagent calculation then?
How many are produced? And you don't have them?
Because you have more than one equation.
You have more than one equation. So you know you have a limiting reagent calculation to do because you saw the work.
Because
I don't like that.
you have more than one amount given.
There we go. Looking at the question, how do I know I need to be concerned about a limiting reagent calculation? I'm given 2 moles of sodium carbonate, 2 moles of water, 1 mole of carbon dioxide. All of those things come out of the chemical equation. All of those are reactants in this. Since I'm given amounts for each and every single one of those, I should go through and check, is this a limiting reagent calculation? The only way I would know that is if I then test all 3 calculations. And at the end of there it goes. At the end of those 3 calculations, I would say, yes, this was a limiting reagent calculation because the numbers that came out at the end are not all the same. If they'd all been the same, then it wasn't a limiting reagent calculation. And then you'd be like, well, that was annoying. I'd do 3 calculations to find out I didn't have to do 3 calculations. Yes. Okay. Kind of makes sense? How does it get more complicated?
You're going to show us.
Actually, I backed off of it, and I didn't actually show you.
You could have like 10 reagents.
I could do 10 reagents, yes. It could be decomposition. That's just going to change the equation. That's not really going to do much.
You don't balance it first?
I could not balance it. Okay? If I don't balance it, you have to balance it first so that you can get the proper conversion factors running through the middle. Okay? Another option. Did I have to give you moles so that you could do a nice simple conversion? No. What could I have given you? Liters. Grams. Milliliters. All of those different units are things that you have the ability to convert because we've already talked about them and done them again and again and again. You're now just stringing multiple together. This is where it does get challenging. In a show your work, you can expect a bunch of calculations being strung together. Go back and look at the Unit 2 exam. For each of your show your works, you had at least 2 calculations that needed to get shown in each of those conversion steps. Okay? Take a look at the short answer, or not the short answer, what's the other one? Just the straight multiple choice. And the straight multiple choice, if you look at the conversions that you had to do, how many conversions did you have to do for each of the multiple choice? Check each question. Maybe 1 or 2 examples where this isn't the case, but for the most part where you had to do a conversion in the short answer, it was 1 conversion. And only 1. Why? Trying to simplify it. Can you prove to me that you know how to do it in your show your work? Now just use a different unit system. If you can prove that you know how to use that different unit system in the multiple choice and you've shown how to do the setup, you can string together as many as possible. All I'd be doing is being a jerk by stringing multiple more in, which, yes, is true. I'll accept that. Okay? So, multiple choice, be thinking along the lines of, I can get this done in 1 step. Try it in 1 step. Okay? If you look at it and you're like, there's no way this can be done in 1 step, screw you, Mike, fine, I'll do a 2nd step. In the short answer, if you look at it and you're like, I can do this in 1 step, you're wrong. Period. You're wrong. Okay? You can't do it in 1 step for any of the show your work. It's not going to happen. Okay? So, next layer of content, percent yields. Okay? You go through and you did that copper lab last week, right?
Yeah.
You didn't obtain this, but or maybe you did, I don't remember your masses. You obtained 5 grams at the end of that experiment. That was too much? A gram?
0.6.
0.6. You obtained 0.5, because I want to use 5. You obtained 0.5 grams from that lab. Okay? When I went through and did that lab, I obtained 50 grams.
You did it wrong. You got to figure it out.
You took a chunk of iron.
If we now report our results to the mining company is going to agree with who?
You.
Me, really? To get that 50 grams, I needed to mine the planet. Then no. What do you mean no? The most for doing the least amount of work. You guys obtained 0.5 grams from how much of a sample?
2 grams.
A 2-gram sample. I obtained 50 grams, a hell of a lot more than you, but by mining the planet of and so, number 1, I did a horrible job, but let's just say the planet in mass, on the order of 10 to the 23rd grams. Okay? I probably am not the person that should be doing any of the mining, and that you should be. But you obtained a smaller amount.
Through less work.
There's a way to normalize those numbers. We're trying to make sure that we have a fair comparison. The 0.5 to the 50, we just say the numerical value, it would say, well, the 50 should win. But you're now changing your mind and saying the 0.5 should win. And it has to do with some other tangible factor, the sample size that we both evaluated. We had to normalize those results. If you were 0.5 out of a gram, your yield was 50%. 50% of what you did was copper. I got 50 grams out of a really, really big sample. My yield was like fractions of fractions of fractions of percents. Right? You did better than I did. That's the point of percent yields, to normalize comparisons. That's why we do it. Same thing happens with grades. We're trying to normalize it so that we can make fair comparisons of points. If everybody had an exam worth differing points, right, you only got 1 point on your exam, but somebody else got 100 points. Does that mean they did better than you?
Yeah.
Your exam was only worth 1 point. Their exam was worth 50,000. You got 100% of the points, right?
You did way better.
They did not.
They got like.
Right? So we need a way to normalize so that we can make a fair comparison. That's the whole point. Right? So within percent yield, we'll take our actual. What did we actually get? And we'll divide that by the maximum possible. Okay? In the case of your copper sample, it was how much you actually started with. Your theoretical maximum was all that you started with was copper. That would have been a bit silly, but that was your theoretical maximum. Right? So we have to be able to come up with those comparisons to establish this. Right? The units behind this. What are the units on percent? Okay, what is the measurement? Let's try that.
Whichever you're using.
So if I looked at your percent, okay, that was 50. When I said it was 50%, that was actually 50% grams of copper.
50%.
A sample.
That was 50% of copper in the sample.
Right.
There was no measurement unit. It's the substance. Okay? The same thing happens when we look at percent yield. We have to make sure the measurement unit cancels. So when you're given a question, you have to make sure that your units in top are equal to the units on the bottom. And as long as those match up, you're allowed to do that calculation. Okay? So grams per mole, is that going to work as a percent?
Sure.
Are grams and moles the same measurement? No. Grams per mole is not a percent. Okay? Grams per mole doesn't relate the same unit. They're different units. That's not a percent. We have to be the same unit. Okay? What unit do we want to use for actual and theoretical?
The same.
Why grams?
The tangible side.
It's easier. I want to measure the percent of oxygen in this room. Please describe to me how I'm going to measure the mass of the oxygen in this room.
Moles.
So you need to use liters, right?
Okay, if I'm going to use gas, I'm now saying liters, but you guys said grams. Why would I choose grams over liters?
It depends on what you're measuring.
It depends on what I'm measuring. That's the system I'm concerned about. So I decide whatever unit I want to work with, that's the unit I want to deal with. So in the case of the copper lab, you used grams. Why did you use grams? You were using a solid. It's easier to measure a solid in grams. Okay? So it's entirely up to you to decide what unit to use. Okay? Does it have to be grams? No, it could be moles. It could be liters. It could be milliliters. It can be any unit you want as long as the units are the same. Okay? So, 2 moles of sodium hydrogen carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. That sounds kind of familiar.
That's super familiar.
That's super familiar. Yeah, I would say that looks kind of like that. Oh yeah, it does. It's almost exactly like that because we just solved that question. And because you solved it, you now have notes on answers for that, right?
Sure, yeah.
Good, because we'll need that. If 2 moles of sodium, well, I already said all that, and only 0.5 moles of sodium hydrogen carbonate are produced. What is the percent yield of the sodium hydrogen carbonate? Pen work, thank you. So I want percent yield. How do I get percent yield?
The actual over theoretical times 100.
The actual over theoretical. You'll have to watch me on this. I almost always leave off the 100%. I apologize for that.
100% or 100?
It doesn't really matter.
No.
They're both getting at the same thing. Hi. What is the actual yield? 0.5, because that's what I actually obtained. When I ran the experiment, I actually obtained 0.5 moles.
Sodium hydrogen carbonate.
Thank you. NaHCO3.
So would you, for the rest, just add 2 moles of sodium carbonate and the moles of water and the moles of carbon dioxide as your theoretical?
The theoretical. Okay. What did we say the units needed to be on our percent yield?
The same.
The same. Which means for our theoretical, what unit should I end up with? Moles of sodium hydrogen carbonate. If I add 2 moles of sodium carbonate with moles of water with moles of carbon dioxide, what are my units? Different. Okay? It's not moles of sodium hydrogen carbonate. It's this weird conglomeration that we couldn't either condense those units or add those units for that matter. So where do I get the theoretical yield then?
You have to do the equations that we did earlier.
We have to do a calculation. A calculation to determine what?
How many each of them yield in sodium hydrogen carbonate?
The maximum yield, right? What kind of maximum yield? The
Of sodium hydrogen.
theoretical maximum yield. Assuming everything works perfectly, that's what we would get. Okay? So that goes through and says 2 moles of sodium carbonate. If all of the 2 moles of sodium carbonate react, what would my yield be?
So you have to add.
What would my theoretical be?
4.
4. Where'd you get the 4 from? I don't quite accept 2 times 2. Help me out there. Come on.
We have 2 moles of sodium carbonate. So
From the calculation that we ran in the conversion from that last example, right? You wrote out that big long line and it said 4 moles of sodium hydrogen carbonate. Okay. What if we'd assumed 2 moles of water and all of the 2 moles of water reacted? How much would we get? 4 moles of sodium hydrogen carbonate, which we got from the previous question. Right? If I assume 1 mole of carbon dioxide reacted, I would get 2 moles. I look at those numbers and I would say the theoretical maximum that could possibly come out of this was 2 moles of sodium hydrogen carbonate. That's the limiting reactant. To do a percent yield, our theoretical comes back to identifying the limiting reactant. So we asked this question, how do you know you do the limiting reactant? Well, you'd have to be given all this information. Are you given all that information? Yep. Yeah, so what do you have to do? Limiting reactant. On top of the limiting reactant, you have to fold in percent yield. How do you know you need to fold in the percent yield?
It says to you right there, actual theoretical times 100.
I wrote that in. That's a calculation. That was our work. Read the question. What about the question tells you you need to be doing percent yield?
What is the percent yield?
Because that's what you started with.
I didn't read that. Sorry. Because it says solve for percent yield. That's how you know you solve for percent yield. Yeah. Sorry, I was reading the red part. You're right.
0.5
Okay.
2 times.
Which would mean now that we know our actual and our theoretical, we can go through and solve it. We would get 0.5 moles of sodium hydrogen carbonate is what we actually obtained over 2 moles of sodium hydrogen carbonate, our theoretical yield, multiply by 100, and we would get 25%
Sodium hydrogen carbonate.
sodium hydrogen carbonate.
Which is what we did today.
Ish. Just ish is, and that's ish is a stretch.
We were
Yes.
making raspberry water. It tastes like raspberries.
Okay.
It was pink, it was raspberry-ish, it didn't taste like it at all.
Okay. Now I'm following you a little bit better.
It's Paul.
Right? That's our percent yield. Right? So when we go through and run this, the units, you guys told me I needed grams, right? Did we use grams? No, we use moles. Could I have converted it to grams?
Oh, yeah.
Yeah. Would that change anything?
Yes.
It's a percent.
It changes nothing because the units were the same. If I converted one to grams and I converted the other one to grams, they would be counteracting each other, and that gram mole conversion then cancels out. You can do it, no problems with it, but as long as your units are the same, we don't care. They can be any unit we want as long as the units are the same.
It's just too much work.
Okay? That is then percent yield.
You can change it.
Okay? So conversion factors and where to find them. We already talked about this, but it's recognizing where and how to find those individual values. If you want a picture of it, go ahead. If I see people with cameras, that's fine. I'll hold on to it. The measurements, right? Those are the things that we talked about back in Unit 2. Okay? Number of atoms, okay? Subscripts from our formulas. If we're trying to convert, and this one's not the nicest formatting. Okay? We can do conversions between substances using a formula. We can convert between substances from a balanced chemical equation. Okay? If I want to deal with moles, I can do moles of substances between chemical equations. I could also see moles be used to convert to the number of particles, or our units, our pieces. What is our piece in chemistry? Atoms are a piece. What else is another piece? Molecules. All of those are pieces that can come in. So recognizing where to find these pieces or these conversions is what you need to be able to do on this next exam. It's then stringing those conversions to each other.
Which is Monday, right?
Right? This is another way to format, looking at that. The Lib Tutor Center. The Tutor Center has another way to format, looking at those conversion factors and where you can go. They call it the mole wheel because pretty much all of our conversions go back to the mole. It's our central conversion unit. So get everything into moles and you can go out from anywhere you can possibly imagine. After that, real briefly, there's this big old question that we could go through and look at. To go through and process this, what you should do is think about the individual steps behind it. Okay? So I'm just going to leave it at that. That's your individual steps on how you'd go through. This is now scaling it up because we're looking at mass when we go through and solve. When it comes to empirical and molecular formula, that will not be on the exam because we have not talked about it. But I could say, oh, see, look, I talked about it. There it is. Oh, we're done. And it's on the exam. It's not on the exam. I'm just kidding.
Is this in Monday?
If you were curious about steps, there's all your steps that you would need to go through to do to answer that question.